I keep telling you always reduce the symmetry. In particular, never work in continuous time flow, but always work in Poincaré section or set of Poincaré sections. Now, I just gave you some formula, and it looks like this formula is different if I'm using continuous time. It's dimensionally different. Because in discrete time this is n, this is an integer. In continuous time, and this is a sum. In continuous time this has dimension of time, and this is integral over time, so this is proportional to the time, so it just looks different, scales different, etc. So if I'm working in Poincaré section and I find something, for example escape rate or some average, how is that related to what I really care about, this average in continuous time? Do I have to recompute it? Do I have to do all the averaging again using continuous time? Well, there's an incredibly simple relation. So if I compute A in continuous time, then what I'm doing is I'm computing my expectation. Now this calculation doesn't care about the time, it's just whatever I use to compute my expectation value. And in continuous time I'm doing this divided by average over the times weighted by stability of the orbits. If I compute the same thing in discrete time, then the expectation value of A is the same, but now I have to compute discrete times here, which means in these formulas, wherever time appears, there should be an integer. But I just look at these formulas and I realize there's a very simple relation. A in discrete time is the same as A in continuous time. Which is the thing we care about in our physical expectations. Times the ratio Tf over n computed with my formulas. So this guys removes divided by time, and this makes it the correct formula. So all you need to know is compute this once. That's a calculation, you have to do it. Because different system can have wildly different averages over continuous time as opposed to discrete times, which is just counting how you come back. So that's a calculation. But once you have computed it, then you know how to relate all discrete calculations to continuous discrete just by this ratio. That's very cute, and I would not in 1,000 years be able to sit down, guess the form of this answer and publish it as physical letters. Any guess that you would like to make that's kind of physical letter quality or lack of quality would be always on the level of trace formula. It would be always on the level of averaging over things in time. So for example, the probability conservation that's so beloved by quantum care is of that kind. You make some trace average and you look what it does in a long-term limit. Cycle expansions are really brilliant in the same sense the determinants are smarter than traces because they have this minus signs. So what cycle expansions build automatically is if you have computed some cycles up to a given length, from them you have an estimate what the next contribution will be for a longer cycle. You can use this pseudo combination saying that the long cycle is doing something like that. My short cycles are not quite doing it, so they're recurrent. So what long cycle is doing is it's being these are unstable, so you come close, you get kicked away. Then you come close to another short cycle, but it's unstable, so you follow it for a while, you get kicked away, and you get kicked away in precisely such a way that you keep repeating this. So you are being pushed away by the both, so you somehow interpolate between the both. But to be close to them at any time, this has to be very small, this distance, because this is exponentially unstable. To stay for some time t, it will explode. So for a significant part of your trajectory, very close to a shorter periodic orbit, and A is computing on a shorter periodic orbit, and the other one is computed, A12 is computed on some of the both. And it's only in this regime, which happens rather quickly, because once you're exponentially away, you gotta get exponentially close to this guy, that they differ. And for that reason, the shadowing is going to be very good whenever you have a smooth flow.